take a look at how we would graph uh, functions such as quadratic functions, um, exponential functions, uh, logarithmic functions, and power functions, which we know how to graph those now, but uh, we can make them simpler to understand by essentially turning them into a line. Since lines are really easy to find the slope of and make calculations with, as compared to some of these other ones. As we saw, solving for that logarithmic function earlier wasn't the easiest thing in the world. So we're going to look at how to essentially transform these into lines. So quadratic function, which takes on the form ax squared plus bx plus c, we would, instead of graphing x and y on our axes, we're going to graph x and the square root of y to make that into a line. To make an exponential function like a times b to the x into a line, we would have to graph x and the natural log of y. To turn a logarithmic function like a times the log of x plus b, to do that, we would graph the ln of x along with y. And finally, a power function like a times x to the b power, we would do the ln of x and the ln of y in our graph. So we have this data here, and we're told to assume it's a power model, so something like a times x to the b. And if you remember from above, we said that the best way to linearize that would be using ln of x and ln of y. So essentially in our calculator, what we're going to do is we're going to take this data for x, and we're going to take the ln of each function and put it in another list, and we're going to take the ln of each y function and put it in a separate list. But thankfully, our calculator does that for us mostly. So let's first put this data in to our list here. So if you go to edit, let's go to list 1, clear it, and we have 0.5, 1, 1.5, 2, 2.5, 3, 3.5, and 4. And then on our L2, our Y values, let's go up and clear that list. We're going to have 0.38 and 3, 10.1 and 24, 46.9, 81, 128.6, and 192. Now, since we're going to assume it's a power function and we're going to linearize it with ln of x and ln of y, what I'll do is I'll make my list 3 be equal to the natural log, so ln of list 1. So I'll go ahead and put second list 1 and hit enter. You can see it generates a list of all the natural logs of my list 1. And I'll do the same thing for L4, making it ln of list 2. And now, instead of graphing list 1 and list 2, I'm going to look at the graph of list 3 and list 4. So when I go to my stat plot, I can turn this back on and put for my X list, I can put L3, and for my Y, L3, and for my Y list, I can put L4. Where that T came from, but so now let's go to my stat plot. So zoom stat. You can see that data looks like a lot more like a line than it does a power function. So now what we can do is we can use linear regression to model it, and we can. So we'll go to calc under our stat menu and use linear regression, where remember we're doing L3 and L4. We might as well just put it into our y value as well. So we get a 0.999 correlation. And if we look at our graph, you can see that line goes right through those linearized data points. So back to our equation here, we have essentially something you're very familiar with. Instead of dealing with this power function, we've got y equals 2.9, or essentially we'll just say 3x plus 1.1. But these aren't our original y and x. These are actually, we're going to call them y hat and x hat, where y hat equals the natural log of y, and x hat equals the natural log of x. So if we were actually to use this to solve for something, we'd have to realize that the ln of y equals 3 times the ln of x plus 1.1. But notice this equation here is something you're very familiar with. You know the slope of 3, y-intercept of 1.1, whereas you might not have readily been able to figure out some values based on the original function. So that's why linearization is helpful to us. So just real quick, one thing we can actually do with this is also um, simplify this natural log function. So if I take the e to the power of both sides, remember e and ln cancel out, so essentially I get y on the left, and I get e to the 3 ln of x plus 1.1 on the right. I can separate that into e to the 3 ln of x times e to the 1.1, and I can scroll down here. Um, remember the e is going to cancel out an ln, so what we can do there is make this 3 become a power of x. Remember, we're using the reverse rule we've done with logarithms. So we can make this e the ln of x cubed times e to the 1.1. Now the e and the ln cancel out, so we have y equals essentially e to the 1.1 x cubed. When we put e to the 1.1 in our calculator, we get 3 essentially. So we can also develop a power function that says it's about y equals 3x cubed from our original function. So go ahead and try this one out. See if you can linearize it in your calculator and find a function that best fits it.